Welcome to another session. So, biochemical aspects of heavy metals: mercury, cadmium, lead, chromium, and some metallites, arsenite, like that. We're going to learn about this. Biochemical aspects of heavy metals and metallites. First, mercury. Toxicity: mercury is highly toxic, we know that. It can disrupt enzyme systems, inhibit protein synthesis, and cause neurological and kidney damage. Then, bioaccumulation: methyl mercury, a form of mercury, bioaccumulates in aquatic food chains, posing risks to humans who consume contaminated fish. Then detoxification: some microorganisms can methylate mercury, converting it into less toxic forms, which aids in its removal from ecosystems. Then cadmium. Cadmium is a non-carcinogen and can interfere with calcium metabolism. It accumulates in the kidneys and liver. Single competitor: cadmium can replace zinc in enzymes, disrupting their function. Then metallothionein, a protein, helps sequester and detoxify cadmium. Lead toxicity: lead interferes with heme synthesis, disrupts neurological development, and affects cognitive function, especially in children. Then calcium mimic: lead can mimic calcium and disrupt signal transduction process. It is sorted in bones and can be released over time. Then chromium, Cr. Toxicity: hexavalent chromium is highly toxic and carcinogenic, damaging DNA and proteins. Then reduction to chromium 3. Some microorganisms can reduce chromium 4 to hexadeoxychromium 3, aiding in remediation. Then arsenic toxicity: arsenic compounds interfere with enzymes and DNA repair processes. Chronic exposure can lead to cancer and skin lesions. Then arsenate reduction: some microbes can reduce toxic arsenate to less harmful arsenite. Then selenium, essential nutrient. Selenium is an essential trace element required for antioxidant defense systems, thyroid hormone metabolism, and immune function. Then selenoproteins. Selenium is incorporated into selenocysteine. Selenium is incorporated into selenocysteine, a constituent of selenoproteins, which are essential for health. Biochemical aspects of atmospheric pollutants. Carbon monoxide, CO. Toxicity: CO binds to hemoglobin more strongly than oxygen, reducing oxygen transport. Prolonged exposure leads to tissue hypoxia. In case of carbon monoxide, we know that. Then cellular response. Cells respond by increasing production of hypoxia inducible factor, HIF1, to adapt to low oxygen levels. Then ozone, O3. Toxicity: ozone damages lung tissue, leading to inflammation and respiratory problems. It can also affect plant photosynthesis. Antioxidant defense: cells respond by activating antioxidant enzymes like superoxide dismutase, SOD, to counteract oxidative stress. Then peroxyethyl nitrate, PAN. Toxicity: PAN irritates the eyes, nose, and respiratory tract. It contributes to photochemical smog. Then metabolism: PAN is metabolized by enzymes like esterases in the body. Volatile organic compounds, VOC. Health effects: VOCs contribute to indoor and outdoor air pollution, leading to respiratory problems and in some cases cancer. And metabolism: some VOCs can be metabolized by enzymes like cytochrome P450 in the liver. The persistent organic pollutants, POPs. Toxicity: POPs such as PCB and dioxins are highly toxic and can bioaccumulate in food chains, leading to various health effects. Then metabolism: some POPs are metabolized by enzymes like cytochrome P450, which converts them to less toxic forms for excretion. So in conclusion, heavy metals, metallites, and atmospheric pollutants can have significant biochemical effects on living organisms. The next, peroxyacetyl nitrate. PAN irritates the eyes, nose, and respiratory tract. It contributes to photochemical smog. Then metabolism: PAN is metabolized by enzymes like esterases in the body. Volatile organic compounds, VOC. Health effects: VOCs contribute to indoor and outdoor air pollution, leading to respiratory problems and, in some cases, cancer. And metabolism: some VOCs can be metabolized by enzymes like a cytochrome P450 in the liver. Persistent organic pollutants: toxicity, such as PCBs and dioxins, are highly toxic and can accumulate in food chains, leading to various health effects. Then metabolism: some POPs are metabolized by enzymes like cytochrome P450, which converts them into less toxic forms for excretion. In conclusion, heavy metals, metallites, and atmospheric pollutants can have significant biochemical effects on living organisms. These effects range from disruption of essential process to toxicological response. Understanding the biochemical aspects of these substances is crucial for assessing their environmental and health impacts and developing strategies for remediation and mitigation. And carcinogens and air. Carcinogens in the air. Carcinogens are substances that have the potential to cause cancer when exposed to living organisms. Many carcinogens can be found in the air, and exposure to airborne carcinogens poses significant health risks to humans. These substances can enter the respiratory system and, in some cases, lead to the development of cancer. Here are some key airborne carcinogens and their sources. Particulate matter, PM. Sources: PM is a complex mixture of tiny particles and droplets in the air. It can originate from various sources, including industrial processes, vehicle emissions, construction, and natural sources like dust and wildfire. And cancer risk: ultrafine particles can penetrate deep into the lungs and even enter the bloodstream, carrying carcinogens with them. Long-term exposure to PM is associated with increased cancer risk, particularly lung cancer. Then polycyclic aromatic hydrocarbons, PAHs. Sources: PAHs are highly formed during the incomplete combustion of organic materials. They are found in vehicle exhaust, industrial emissions, and tobacco smoke. They can also be produced by natural processes like forest fires. Cancer risk: some PAHs are non-carcinogens. They can bind to DNA, causing mutations and initiating the development of cancer, especially lung and skin cancer. Then volatile organic compounds. VOCs are emitted from various sources, including vehicle exhaust, industrial processes, and the use of household products like paints and solvents. Then cancer risk. Some VOCs, such as benzene and formaldehyde, are classified as human carcinogens. So, prolonged exposure to high levels of these compounds can increase the risk of leukemia and other cancers. Then, radon gas. Radon is a naturally occurring radioactive gas that results from the decay of uranium in the earth crust. It can seep into homes and buildings through cracks in the foundation. Cancer. Radon is the second leading cause of lung cancer after smoking. When inhaled, it decays and emits alpha particles that damage lung tissue and DNA. Then asbestos fibers. Asbestos is a group of naturally occurring mineral that were once widely used in construction materials, and in some places it's still very relevant. And when these materials deteriorate or when they are disturbed, asbestos fibers can become airborne. Inhalation of asbestos fibers can lead to lung cancer, mesothelioma, and other respiratory diseases. Asbestos exposure is a well-established cause of cancer. Then diesel exhaust particles. Diesel exhaust is generated by diesel-powered vehicles and machinery. It contains a mixture of gases and particles, including PAHs and other carcinogens. Cancer risk. Diesel exhaust has been classified as a Group 1 carcinogen by the International Agency for Research on Cancer, IARC. Prolonged exposure increases the risk of lung cancer. Tobacco smoke. Mainstream and secondhand smoke from tobacco products contain over 700 chemicals, many of which are known carcinogens. Cancer risk. Smoking is the leading cause of preventable cancer worldwide. It is linked to lung, mouth, throat, esophagus, and other cancers. Then migration and prevention. Preventing exposure to airborne carcinogens is crucial for reducing cancer risks. This can be achieved through stricter regulations and emission controls in industrial and transportation sectors. Promoting the use of cleaner fuels and technologies, indoor air quality improvements such as proper ventilation and use of air purifiers, smoking cessation programs to reduce tobacco-related cancer risks, then public awareness and education on the dangers of airborne carcinogens. So in conclusion, airborne carcinogens pose significant health risks, with lung cancer being one of the most common outcomes of exposure. Mitigation efforts, regulatory measures, and public awareness campaigns are essential for reducing cancer risk associated with this harmful substance in the air. Then principles of analytical methods. Titrimetry. Principles of titrimetry, also known as titration, is a quantitative analytical technique used to determine the concentration of a specific substance, the analyte, in a sample. It is based on the reaction between the analyte and a reagent or a titrant of known concentration. Stoichiometry is very important. Titrimetry relies on stoichiometry, which is the balanced chemical equation that describes the reaction between the analyte and the titrant. The equation indicates the mole ratio between the reactants. For example, in an acid-base titration, the stoichiometric equation might be HCl plus NaOH gives NaCl plus H2O. An equivalence point. The equivalence point is the point in the titration where the stoichiometrically equivalent amounts of the analyte and titrant have reacted. It is determined by the mole ratio from the stoichiometric equation. At the equivalence point, the reaction is complete and the amount of titrant required to reach this point is used to calculate the analyte's concentration. An indicator. In some titrations, an indicator is used to visually signal the equivalence point. An indicator is a substance that changes color in response to changes in pH. The choice of indicator depends on the type of titration being performed. For example, phenolphthalein is commonly used as an indicator in acid-base titrations. It is colorless in acidic solution and turns pink at the equivalence point, pH around 8.2. And standardization will be performing. Before titration, the titrant's concentration must be accurately determined through a process called standardization. This involves titrating a known quantity of a primary standard, a highly pure and stable compound, with the titrant. The result of standardization allows for the precise calculation of titrant's concentration, ensuring accurate titration results. Then endpoint. The endpoint is the point in the titration where a noticeable change occurs, indicating that the equivalence point is near. In the presence of an indicator, the endpoint corresponds to the indicator's color change. The endpoint may slightly differ from the true equivalence point, so careful observation and technique are required. Then calculations. After the titration is complete, the amount of titrant used is used to calculate the concentration of the analyte. The calculation depends on the stoichiometry of the reaction. The formula used for calculation varies with the type of titration, acid-base, redox, complexometric, and the specific analyte being determined. Then titration curves we will be plotting. Titration curves are graphical representation of the pH or other relevant property of the solution being titrated as a function of the volume of titrant added. These curves provide valuable information about the titration process. Then precision and accuracy. Precision refers to the reproducibility of results, while accuracy refers to how close the results are to the true value. Careful technique, precise measurement, and standardized procedures are essential for achieving both precision and accuracy in titrimetry. An application, titrimetry is widely used in analytical chemistry for various applications, including the determination of concentrations of acids, bases, redox active substances, metals, and complex ions. So principles include principles of stoichiometry, equivalence points, indicators, standardization, and careful calculations. These are commonly used in qualitative and quantitative analysis. Okay. Then gravimetry and bomb calorimetry. Gravimetry is a quantitative analytical technique that involves the determination of the amount of a substance in a sample. It relies on the principles of mass conservation and stoichiometry. We've just mentioned this. Gravimetry is a quantitative analytical technique that involves the determination of the amount of a substance in a sample based on the measurement of mass. It relies on the principles of mass conservation and stoichiometry. Fundamental principles include principle of gravimetry, that is the precipitation reaction. Gravimetric analysis begins with the addition of a reagent to a sample, causing a chemical reaction that leads to the formation of an absolute precipitate. The choice of reactant is crucial and depends on the specific analyte being determined. Then precipitate separation. The resulting precipitate is separated from the solution using techniques like filtration or centrifugation. So proper separation is essential to ensure the purity of the precipitate. Then washing and drying. The collected precipitate is carefully washed to remove any impurities or soluble substances. After washing, it is dried to a constant mass under controlled conditions. Then weighing. The dried precipitate is weighed with high precision using an analytical balance. The difference in mass before and after precipitation corresponds to the amount of the analyte in the sample. So calculations. Calculations involve stoichiometry to determine the analyte's concentration or mass in the original sample. The molar mass and chemical formula of the precipitate are used in these calculations. Then applications of gravimetry. Gravimetry is widely used in various analytical applications, including the determination of metal ions in ores and alloys, non-metallic compounds in minerals, proteins and organic compounds in biochemistry, impurities in pharmaceuticals, residues of contaminants in environmental analysis, Bohm colorimetry. Bohm colorimetry is a technique used to measure the heat of combustion of a substance with high precision. It is primarily applied in the field of thermodynamics and calorimetry to determine the energy content of various materials, especially in the study of fuels. Here are the fundamental principles and steps of Bohm colorimetry. Principles include combustion reaction. The substance under investigation, usually a fuel, is placed inside a Bohm colorimeter, which is a strong sealed container. It is then ignited in the presence of excess oxygen to ensure complete combustion. After that, heat transfer will be taking place. So during combustion, the substance releases heat energy, which is absorbed by the colorimeter vessel, including its contents, that means water or other heat absorbing medium. Then temperature measurement. The temperature change delta T resulting from the combustion is precisely measured using a thermometer or a thermocouple. This temperature change is directly related to the heat of combustion. Then calibration. Calibrations are performed using known standards to relate the temperature change to the energy content. Then calorimeters are often calibrated using substances with well-established heat values. Then we need calculations. The heat of combustion, enthalpy change delta H, is calculated using the temperature change, calorimeter constants, and the heat capacity of the calorimeter system. Then we need applications of Bohm calorimetry. Bohm calorimetry is commonly used in various scientific and industrial fields, including determining the calorific value of fuels such as coal, natural gas, and biofuels, and studying the thermodynamic properties of chemical reactions, measuring the energy content of food products, and investigating the efficiency of combustion process in engines, etc. So gravimetry is a quantitative analytical method used based on the measurement of mass and is used to determine the amount of a substance in a sample. Bohm calorimetry, on the other hand, is a technique for measuring the heat of combustion of a substance. Both methods are fundamental in analytical chemistry and are employed in a wide range of applications, from determining analyte concentrations to studying energy content. Understanding these principles is essential for accurate and reliable analytical measurements. Then chromatography, paper chromatography, thin layer chromatography, gas chromatography, and HPLC. HPLC in the sense high performance or high pressure liquid chromatography. So first is about chromatography. What is chromatography? Chromatography is a versatile and widely used technique in analytical chemistry for separating, identifying, and quantifying components within a mixture. It relies on the different distribution of analytes between a stationary phase and a mobile phase. The technique is based on the principles of absorption, partition, or affinity, depending on the type of chromatography being used. Then paper chromatography, principles of paper chromatography. Stationary phase. In paper chromatography, the stationary phase is a piece of specialized paper. The paper can be chemically modified to contain specific absorbents that interact with analytes. Then mobile phase. The mobile phase is a solvent that moves up the paper via capillary action. It carries the sample mixture through the paper. Then sample application. A small amount of the sample is applied as a spot or line near the bottom of the paper. A sample contains various components that will separate as they move up the paper. Then separation. As the mobile phase travels up the paper, it carries the sample components with it. Components with different affinities for the stationary phase will travel at different rates, leading to separation. Then we will be performing visualization. So after chromatography is complete, the paper is dried and the separated components are visualized by methods like UV light iodine vapor or specific staining reagents. In some cases, some chemical reagents like ninhydrin are sprayed into that paper to view the specific components with the help of color change. And applications of paper chromatography: separation and identification of amino acids, dyes, and pigments. Analysis of plant pigments, chlorophyll. Examination of the composition of inks, food dyes, and pharmaceuticals. Then thin layer chromatography, TLC. Principles of TLC: stationary phase. In TLC, a thin layer of an absorbent material such as silica gel or alumina is coated on a glass or plastic plate. This thin layer serves as a stationary phase. Then mobile phase. Similar to paper chromatography, a solvent acts as the mobile phase. It moves up the plate via capillary action. Then sample application. The sample is put near the bottom of the TLC plate. As the solvent travels up the plate, it carries the sample components. Then separation occurs due to differences in absorption and partitioning between the stationary and mobile phase. Then we will be performing visualization. After separation, the TLC plate is dried and visualized under UV light or chemical reagents specific to the analytes. Then application of TLC: identification and separation of organic compounds and mixtures, purity assessment of synthesized compounds, monitoring reactions and assessing the progress of chemical synthesis. Gas chromatography. Principles of gas chromatography: stationary phase. In gas chromatography, the stationary phase is the high boiling point liquid, often immobilized on a solid support or a solid absorbent packed into a column. Mobile phase. The mobile phase is an inert carrier gas, helium or nitrogen, that flows through the column. Sample injection. The sample is injected into the GC system where it is vaporized and introduced into the column. Then separation. Components in the sample interact with the stationary phase as they pass through the column. Separation occurs based on the differences in partitioning between the stationary and mobile phase. Then detection. Analytes exist in the column at different times, that means retention times, and are detected by a detector, flame ionization detector or mass spectrometer. In applications of GC, quantitative analysis of volatile organic compounds, VOCs, separation of complex mixtures in petrochemical, environmental, and pharmaceutical analysis, classification, identification of organic compounds in forensics and food analysis, high performance liquid chromatography, HPLC. Principles of HPLC include stationary phase. HPLC uses a column packed with fine particles of a stationary phase, typically silica based material. Then mobile phase. The mobile phase is a liquid solvent, often a mixture of water and organic solvents, delivered at high pressure through the column. Then sample injection. The sample is injected into the HPLC system and it passes through the column. Then separation. Analytes interact with the stationary phase in the column. Separation occurs based on differences in partitioning and absorption. Then a detection. Analytes exist the column at different times and are detected by various detectors, including UV, vis, fluorescence, or mass spectrometry. And applications of HPLC: analysis of a wide range of compounds, including pharmaceuticals, proteins, nucleic acids, and environmental pollutants. Quantitative and qualitative determination of analytes in complex mixtures. Purity assessment of drugs and pharmaceuticals. So in conclusion, chromatography encompasses a wide range of techniques that rely on the differential interaction of analytes with the stationary phase and a mobile phase. These techniques are essential for quantitative and qualitative analysis in various fields of chemistry, providing valuable insights into the composition of complex mixtures and the identification of individual components. So understanding these principles is crucial for their successful application in analytical chemistry. Next is about flame photometry, spectrophotometry. Flame photometry. Simple atomization. In flame photometry, the sample is aspirated into a flame, usually an air acetylene or air acetylene nitrous oxide flame. The high temperature of the flame atomizes and excites the analyte atoms. Then emission spectroscopy. As the atoms return to their ground state from excited states, they emit characteristic wavelengths of light. These emitted photons are specific to each element. Then wavelength selection. A monochromator or interference filter is used to select a specific wavelength of light that corresponds to the element of interest. Then intensity measurement will be performed. The intensity of the emitted light at the selected wavelength is measured by a photodetector. Then we will be performing quantification. The intensity of the emitted light is directly proportional to the concentration of the analyte in the sample. Calibration curves are used for quantification. An application of flame photometry, quantitative determination of alkali and alkaline earth metals, sodium, potassium, and calcium in solutions, widely used in clinical laboratories for analyzing blood and urine samples. And spectrophotometry principles: absorption of light. Spectrophotometry measures the absorption of ultraviolet and visible light by molecules in a sample. Analytes absorb specific wavelengths of light. And wavelength selection: a monochromator allows the selection of a specific wavelength of light, often in the UV or vis rate, depending on the analyte. A beam of light passes through the sample and the intensity of transmitted light is measured. The increase in intensity or absorbance is directly related to the concentration of the analyte. Then Beer-Lambert law. Spectrophotometry follows the Beer-Lambert law, which relates absorbance, concentration, molar absorbability, and path length. Applications of UV-Vis spectrophotometry: quantification of chromophoric compounds, dyes, pigments, and biomolecules like DNA and proteins. Drug analysis in pharmaceuticals. Environmental analysis, monitoring water quality, atomic absorption spectrometry. Principles of AAS, sample atomization. AAS atomizes the sample by heating it in a flame or in a graphene furnace. The temperature causes the analyte's atom to transition to higher energy states. Absorption of light. AAS measures the absorption of light at a specific wavelength that corresponds to the electronic transitions of the analyte atoms. Then quantification. The absorbance is proportional to the concentration of the analyte. Calibration standards are used for quantification. Then applications of AAS: determination of trace metals and metalloids in environmental, geological, and clinical samples. Quality control in food and beverages. Inductively coupled plasma atomic emission spectroscopy. Principles of ICP-AES: sample atomization. This requires high temperature. Inductively coupled plasma as the atomization source. The plasma atomizes and excites the analyte atoms. Then emission spectroscopy: as analyte atoms return to their ground state, they emit characteristic wavelength of light. This emitted light is detected and measured. Wavelength selection. A polychromator allows the simultaneous measurement of multiple wavelengths, providing a complete emission spectrum. Then quantification. The intensity of emitted light at specific wavelength is proportional to the analyte concentration. Calibration curves are used for quantification. Applications of ICP-AES: multi-element analysis of metals and non-metals in a wide range of samples, including environmental, geological, and biological specimens. Elemental analysis in metallurgy and material science. Inductively coupled plasma mass spectrometry. Principle ICP-MS. Principles of ICP-MS. Sample introduction. The sample is introduced into an ICP where it is atomized, ionized, and converted into ions. And mass analysis: ions are separated based on their mass to charge ratio using a mass spectrometer. Detection is performed at multiple mass values. Then quantification: the number of ions detected at each MYZ value is proportional to the concentration of the corresponding element. So calibration standards are used for quantification. Then application of ICP-MS: ultra trace element analysis, including isotopic analysis and quantification of rare elements, radioactive isotopes, trace metals, geochemical analysis, forensic science, and environmental monitoring. So in conclusion, flame photometry, spectrophotometry, atomic absorption spectrometry, inductively coupled plasma atomic emission spectroscopy, along with inductively coupled plasma mass spectrometry are powerful analytical techniques used for quantifying elements and molecules in various samples. Each technique has its own principles and applications, making them essential tools in analytical chemistry and scientific research. The next is about electrophoresis, XRF, XRD, NMR, etc. Electrophoresis principles. Electrophoresis relies on the movement of charged particles, ions, molecules, or particles in an electric field. When a voltage is applied across a medium, it creates an electric field that drives the movement of charged species. Separation based on charge and size. Electrophoresis separates analytics based on their charge and size. Positively charged species move towards the cathode, negative electrode, while negatively charged species move towards the anode, positive electrode. Gel or capillary medium. Electrophoresis can be performed in a gel electrophoresis, or within a capillary electrophoresis. The choice depends on the application and the type of sunlight being separated. Then we will be visualizing that. After electrophoresis, the separated components can be visualized by staining with specific dyes, allowing for quantitative and qualitative analysis. Next application we will be dealing in the next session. Thank you for listening.